Today, we're going to decode the secret language of motion. We're going to see how a few simple lines on a graph can tell the entire story of an object's journey, from a steady gallop all the way to a sudden sprint.
I mean, really think about that for a second. Every single time you walk or run or even drive your car, you're creating a story of your position, your speed, and your acceleration. Well, motion graphs are the language we use to write that story down, and by the end of this, you're going to be totally fluent.
All right, let's start with the simplest story you can tell: constant velocity. I want you to picture this: a graceful llama just enjoying a nice, steady gallop. No speeding up, no slowing down, just smooth, constant motion. So our llama's speed isn't changing one bit. It is locked in at a steady 3 meters per second. So the question is, how do we translate that simple movement into the 3 different types of motion graphs we use?
Okay, let's start with acceleration. Since the llama's velocity is totally constant, its acceleration is, well, it's nothing. It's 0. So the graph is just a flat line right there on the x-axis. No change in velocity means 0 acceleration. It really is as simple as that.
Next up, the velocity graph. This one's pretty straightforward. Since our llama is moving at that constant 3 meters per second, the graph is just a simple horizontal line at a value of 3. Time keeps ticking by, but that velocity, it stays exactly the same. And finally, we have the position graph. This one shows us how far the llama is moving from its starting point. Because its velocity is constant, it covers the exact same amount of distance every single second. This creates a perfectly straight, upward sloping line.
And that slope brings us to our very first golden rule. The steepness, or the slope, of a position-time graph tells you the object's velocity. A totally flat line means 0 velocity. It's not moving. But the steeper that line gets, the faster the object is going.
Okay, that was fun, but let's be real. Things rarely move at a constant speed forever. Let's make the story a little more exciting. Let's meet our next character, an alpaca. And now we're introducing acceleration.
So our alpaca is just standing there, minding its own business, and then, whoa, a capybara appears. The alpaca bolts, accelerating at a constant rate of 1 meter per second squared. Now what does that mean? It means every single second its velocity increases by 1 meter per second. This one change, it changes everything about our graphs.
Let's look at the graphs. The acceleration is constant, but it's not 0 this time. It's a steady 1 meter per second squared. So the acceleration graph is, you guessed it, a horizontal line, but this time it's up at a value of 1.
So what does that constant acceleration do to the velocity? Well, since the velocity is increasing by the same exact amount each second, the velocity graph isn't flat anymore. Nope, it's now a straight upward sloping line. Makes sense, right?
And here, this is the big reveal. The position graph is now a curve. But why? Because the alpaca is covering more and more distance each second as it gets faster. Remember our first rule? The slope of this graph is the velocity. So since the velocity is constantly increasing, the slope of the position graph has to get steeper and steeper and steeper, creating this beautiful upward curve.
And that right there gives us our second golden rule. Just like the slope of the position graph is velocity, the slope of the velocity graph is acceleration. It's literally telling you how quickly the velocity itself is changing.
So we've seen 2 different stories play out. Now let's just hit pause and build our universal toolkit. These are the rules that will let you decode any motion graph you ever see. I promise.
This, right here, is your cheat sheet. As we already know, the slope of a position graph is velocity, and the slope of a velocity graph is acceleration. But there's another powerful tool, the area under the curve. For a velocity graph, the area tells you the displacement, basically how far the object has traveled. For an acceleration graph, the area tells you the total change in velocity. Think of it this way. Slope shows you the rate of change at any one moment, while area shows you the total amount that has accumulated over time.
So, what about those curves on the position graph? Here's a super simple trick. If the curve opens upward, kind of like a smiley face, the acceleration is positive. If it opens downward, like a frowny face, the acceleration is negative. It's a really quick visual check to see which way the velocity is changing.
Now listen up, because this is absolutely crucial. A horizontal line on a position graph means the object's position isn't changing, it's at rest. But a horizontal line on a velocity graph means the velocity isn't changing, so it's moving at a constant speed. That is a huge distinction and a very, very common trap to fall into.
All right, you have the toolkit, you know the rules. So let's take it for a spin on a much more complicated journey. You think we can read the full story from just one graph? Let's find out.
Okay, here it is. A velocity versus time graph for our alpaca. As you can see, this journey has multiple parts. The line goes up, it flattens out, it goes down, it even crosses the axis and keeps going. Let's break this thing down piece by piece.
Let's break it down. Okay, step 1, from 0 to 2 seconds. The slope is positive, the line's going up. So the alpaca is speeding up. Step 2, from 2 to 3 seconds, the slope is 0, the line is flat. It's cruising at a constant 20 meters per second. Step 3, from 3 to 5 seconds, now the slope is negative. It's slowing down, and right at the 5-second mark, it comes to a complete stop. But look what happens in step 4. The velocity goes negative. The alpaca has actually turned around and is now speeding up in the opposite direction. A complete, complex story, all from that one line.
And just like that, you've learned the grammar and the vocabulary of motion. You can now speak the language. So let's just do a super quick recap of the fundamental rules we've covered.
Okay, if you remember nothing else, remember these 3 key takeaways. First, the slope of a position graph tells you velocity. Second, the slope of a velocity graph tells you acceleration. And third, the area under a velocity graph tells you displacement. With just these rules, you can decode the story of pretty much any journey.
So I'm going to leave you with a final thought to take with you. Think about your drive or your walk to work or school this morning. The speeding up, the slowing down, the stops at traffic lights, the cruising along at a constant speed. What would that whole story look like as a graph? The cool thing is, you now have the tools to actually draw it.